now. Our next speaker is Doina Precup, who is going to tell us about fast reinforcement learning with generalized policy updates. So please, Doina, take it away.
Thank you very much. And before I start, I just want to say thank you to the organizers of this workshop. I found the schedule really inspiring and interesting this whole week. And it's really nice to have this in these difficult circumstances. So I will talk about a recent PNS paper, actually, and this is joint work with Andre Barreto, Shalbohu, Diana Borsha, and David Silver, my colleagues at DeepMind. And the motivation for this work is really that we would like to have reinforcement learning agents that become generally capable AI agents. And I always use cooking as an example, partly because I would like other people to do more cooking for me, perhaps, but also because I find it a good illustration of this idea that you need to have agents that can quickly adapt to unforeseen circumstances and can improvise and learn how to do things with very little new data. So ideally, we would like to have reinforcement learning agents that can build policies and can build predictions over time, and then reuse them as necessary. So just to give you an example, it's about to be my daughter's birthday, and my youngest daughter wanted to bake her a cake, but as it turns out, we have no flour in the house. And so now she has to improvise something that is kind of like a cake, but involves no flour, which is one of the main ingredients. And she's actually doing a great job of that, I have to say. But a reinforcement learning agent may not be able to do this. And so the work that I'm going to talk about is trying to move us in the direction of having reinforcement learning agents that can easily transfer their knowledge, recombine their knowledge in the face of a changing world and in the face of unexpected circumstances. And in order to do this, we're going to build on the foundation of policy evaluation and policy improvement, which are in some sense the bread and butter of all dynamic programming algorithms, and so by extension also reinforcement learning algorithms. So imagine you have a Markov decision process, you have some policy pi in this Markov decision process. Policy evaluation and policy improvement, you can think of these as two operators that map between policies and value functions. So policy evaluation takes a given policy pi and computes the associated value function, whether over states or over state action pairs, Q. And policy improvement is going to take a value function and then compute out of it an improved policy by using a maximization operator. And when we do policy improvement, we have quite an interesting guarantee, which says that the new policy obtained, denoted pi prime in these slides, is better than the old policy pi that we had at all states. Now, you're going to notice here in the slides that I'm using the standard notation, except I've put a subscript to all the value functions, a little R subscript. R denotes the reward function, and this is going to come in handy because I would like to think about generalization for different reward functions, and so we're going to parameterize R later. So in dynamic programming, we often have a model of the environment, and we then do policy evaluation and policy improvement exactly and interleave these steps. In reinforcement learning, we don't have a model of the environment, and so we do approximate policy evaluation and approximate policy improvement, and again, interleave them somehow. And so this is just a picture to sort of visualize what's going on. An agent might start at a policy pi 1 here. Policy evaluation takes pi 1 and maps it into the space of value functions. And then policy improvement takes a value function and maps it back into a policy. And so these steps will be interleaved. And eventually, if we have a finite Markov decision process and we have a perfect model, we'll end up with an optimal policy, pi r star, and an optimal value function for this particular reward function. And the other picture here, the square picture, is a similar visualization, but just in value space. And we have only two states. And so any particular value function is a dot here in this square. And the orange trajectory is the orange trajectory through value space. Okay, so if we start with the value of some particular policy pi 1, and we do policy improvement, we will end up with a policy pi 2 that has to be in this shaded area because it has to be better at all states. And so one way to think about policy improvement is that we have these sort of squares or rectangles that are included in each other, and eventually we'll end up with the optimal value function VR star. So what I'm going to do in this talk is actually to generalize this process both to multiple reward functions, so multiple R's, as well as multiple policies pi. Okay, so this is going to lead us to generalized policy evaluation and generalized policy improvement. So I'll describe these operators and I'll show some empirical results that use this type of method. And why would we want to do this? Well, multiple policies might be learned by the agent during its lifetime ahead of time. And so if we have a way to combine the knowledge in these policies very quickly, that might be useful. And multiple reward functions is something that is, of course, very useful for multitask learning, where you have an agent that's always in the same dynamics, right? The probability distribution stays fixed, but the reward changes over time. But a different way to think about it is, even if you have a fixed environment that is really, really big, where the agent has sort of trouble traveling everywhere, at some point it might end up in some new states, and that's as if you had a new reward function. So what are generalized policy updates? We're going to do generalized policy evaluation and generalized policy improvement, and these are going to be very similar to the ones that we do with single policy and single reward function. Specifically, generalized policy evaluation is going to compute the value of some policy, but for an entire set of reward functions. Okay, so capital R here denotes the set of reward functions. Generalized policy improvement is going to take a set of policies, big pi, and some given reward function, and compute a new policy pi prime that is better than what we had before for this specific reward function. And so the guarantee here that we have is very related to the one we had for usual policy improvement, except we have an added suprema over the space of policies here. Okay, so the guarantee is that the value of pi prime is going to be better than the value that I would have obtained with any of the policies in my given set. And of course, if we just have one reward function R and one policy pi, then we just recover usual policy evaluation and policy improvement. So let's visualize a little bit what's going on here. So we're going to have a space of policies, big pi over here. There, for example, there are two policies in my space right now. There's also a space of possible value possible reward functions, big R. And in this particular case, there are 3 different reward functions in this space. Okay. GPE, generalized policy evaluation, computes the value of one policy, say pi 1 in this case, in all of these different tasks. And I'm going to talk in a minute about how we can do this efficiently in certain cases. GPI, the policy improvement operator, lives in one of these tasks, and it's going to take value functions for multiple policies and compute something that is better than all of them, not necessarily optimal. Okay, and so for example, if you look at task R1, what does this guarantee mean? It means that if I have these 2 value functions, these 2 rectangles, GPI is guaranteed to give me something that's inside their intersection. Okay. Now, in the middle, you have a situation where the policy is actually, one of them is better than the other. In that case, GPI is not going to do anything except select the better policy. Okay. And of course, ideally, I would like to be in a situation like in task 3, where the space that I end up with here is very, very small, right? This means that I've done a lot of improvement. Okay, so this is sort of the intuition of what we're going to do. We now have to spell out a little bit more about how we're going to carry out the GPE and GPI, these 2 different operators. And the first thing that we're going to talk about is generalized policy evaluation. And the intuition that we're going to use here is that if there was a way to describe the reward function R, and then to have a nice mapping from R to Q pi R for any pi, then actually generalized policy evaluation would be very efficient. We would learn this mapping, right? And then we could just use it. And we could very easily evaluate a policy, a given policy pi for any reward function. Now, this is going to be hard to do in general, but assume, for example, that the reward is actually linear in some kind of feature space phi. Okay, so the reward function can really be described by a parameter vector W, and the reward of any state is just W dotted with the features at that state. So then the space of all reward functions R phi is just described by the space of these parameters W. Okay. Now, phi could be very complicated. Phi could be, I don't know, the first layers of a convnet or something like this. But the dependence of the reward is only linear here. So in this case, we already know from the prior work of Andre Barreto and colleagues that there is a nice way to represent the value function by using successor features. Okay, so successor features are the expected value of the feature vectors cumulated and discounted over time. Okay, so psi pi of a state action pair is just cumulating the feature vectors phi of all the state action pairs that are coming afterwards, discounted. Okay, and this is just like a regular value function, can be estimated, for example, by TD methods. And there are some interesting special cases of this. For example, the successor representation of Peter Diane is obtained here if phi is just a one-hot indicator. Now, if we compute the successor features, then actually the value function for any particular linear reward, q pi w here, can just be obtained by taking w and dotting it with the successor feature representation. And this is, again, work that's been done by Andre Barreto and colleagues that appeared in Europe's a few years ago. So this is now a special case where we can do policy evaluation very quickly, basically by taking our reward function and mapping it using successor features into a value function. The successor features will need to be pre-computed, but we can do this once at the beginning of time for policy pi, and then we can use them thereafter. Right? This is, again, under the assumption that the transition dynamics of the environment stay the same. Note also that the successor features are actually a form of model of the environment, because they sort of encode this expectation, but over the dynamics. Now, how are we going to do generalized policy improvement? Well, this is actually pretty easy. It's just like the policy improvement operator that you normally have, except instead of just taking a max over actions, we're also going to take a max over policies in our policy class. And for the purpose of this talk, I'm only using discrete policy classes. So I have 2, 3, 4 policies. So actually taking this max here is not going to be very expensive. I think if the policy class is complex, then maybe this operation needs to be thought of a little bit more. Okay, so this is just the usual, almost the usual policy improvement. I want to make a couple of remarks. One is that pi prime may end up, because of this argmax, choosing actions that are not actually chosen by any of the policies in the policy class, right? So for example, if in my policy class I have 2 policies that are attracted to some area of state space, the argmax, if what I want is to be repulsed by that area of state space, will be some other action, okay? And so there is no sense in which pi prime is limited by the choices that are in pi. The other interesting aspect of this is that this process is actually going to be done after one iteration, because it squeezes the knowledge out of the action value functions, and then no other changes will happen. Okay. If I wanted to do more iterations, the value would need to change. Okay. But in this process, we're assuming that we're pre-computing for some set of policies pi, and pi prime does not necessarily become part of this, and we're not going to recompute its value necessarily. That would require extra data, and that would allow us to iterate. But in all of the results that I will show, we only do this once. Okay. So here's a little illustration. This is a little grid world task where you have an agent there's red objects and blue objects. And we're going to consider, for example, one reward function, which is being attracted by red objects, okay? And another reward function, which is being attracted by blue objects, and then a reward function that likes red but not blue, okay? And so one way to think about this is that we have the features, which are red and blue objects, and we're going to make a linear weighting over these features. So W1 is a weight vector that says I like red and I'm indifferent to blue. W2 says I like blue, and W3 says we like red, we don't like blue. Okay, and the little shaded areas are showing you trajectories that these policies will produce if the agent is this little yellow circle. Okay. So one interesting thing to note here is that you can think of W essentially as a preference function over features. Okay, that's very clear in this example. Which features do you like? Which features do you not like? And we can pre-train policies, essentially maximizing those features ahead of time. So in a lot of the experiments, for example, we pre-train pi1 and pi2, okay, which are these two policies that like red objects and blue objects, and we use them as the basis for transfer. The way that we're going to do the transfer piece is by doing GPE and GPI. Now, there's a couple more interesting things to think about. One is, what if we actually don't know the preference vector W, okay? Well, that problem is easy to solve by regression, right? We can just take tuples, state, action, and reward. These are single state tuples. And we've made the assumption that the reward is a linear function if we consider phi being given. And so we can just solve a regression, and you can put in, squared error or any of your favorite regression targets here and solve for W tilde here. So think of this as the task inference step. Now, what if we don't also know the right features? Well, then maybe what we need to do is to look at multiple tasks, okay? And so here we consider a problem where we're learning both the features, phi tilde, as well as the weightings, W tilde, okay? And it's just a sort of a nested regression. And notice that to solve this problem, you can make any arbitrary choices about phi tilde. So in particular, we can choose that to be a neural net and build complexity in it.
Doina, I'm going to jump in just to say you've got about 4 minutes left.
Sounds good.
All right. Thank you.
Okay, so here are some the environment that I was showing you before. We can train Q-learning to solve this environment. We're looking at task W3. So you like red, you don't like blue. We've pre-trained policies that like red and like blue. We've pre-trained them with 5 times 10 to the power 5 time steps. And we've pre-trained their both the policy as well as the successor features. Q-learning here, the horizontal dashed line, you can think of that as the optimal performance. This has been trained by 10 to the 6 sampled transitions, okay? And now we can do GPE and GPI, or you can train Q-learning from scratch on the new task, okay? And so Q-learning, of course, eventually will reach the optimum performance, but it will take a very long time. Whereas if I know the W, then of course we can take our two policies and do GPE and GPI immediately, and we get this horizontal blue line in the graph. And if we don't know W, we need a few time steps to get some data to do the regression. And so that's the little dashed blue line here. And you can see that this converges really, really quickly. The other thing you have to notice is that we are making a trade-off between the quality of the final solution and the sample size, okay? These processes are extremely fast, right? Orders of magnitude faster than Q-learning, but of course, they're not going to end up with the same performance as Q-learning. If you have enough transitions, then you should do Q-learning in this particular example and you get to the right solution. But we're making this trade-off very quickly. We are in the very small sample regime. The other picture is sort of zooming in at the very beginning of this trajectory and actually looking at learning both W as well as phi and phi of different dimensions. And you can see that this problem is actually quite easy. Again, this is essentially a supervised learning problem. And so we can do this really, really quickly. This graph here is a little bit mysterious, but what we're trying to show is the effect of the policy set, okay, on this process. Obviously, intuitively the policies matter. And figure A is looking at some different initial policies. All of the policy classes are disjoint, and the red, green, and blue lines here are each a policy class. And the W's that you see are the W's for the policies that have been included in these sets. Okay, and the dashed lines are just Q learning after seeing amounts of data. And again, when we're doing GPI, this is an immediate process because in this case we're providing W, so it's a zero shot, requires no further data. And what you can see, and the farther away you are from the center, the more reward you're getting. Okay. And so what you can see is that, yes, there are some policies like, this blue set, for example, provides good performance on all different tasks. Okay. Other sets are perhaps a little bit less good. Figure B is a situation where we start with one policy and then we keep adding policies. So each of these sets has more and more policies added to them. And again, performance increases. But in this case, at least at the beginning, your performance will be best if you're looking at policies that are similar to the ones that you had in the training set. But really, performance can be good for quite different policies that are from a spectrum of different locations in this case. The other thing that we can do is actually infer the preference vector, so infer the W. Because the agent's preferences really could vary over time. So if you imagine this example that I was talking about, and imagine that the task is always to pick up the object that appears more in the grid world. So if there's more red objects, you want red, but otherwise you want blue. Then actually you should modify your preferences over time. And of course, we can think of this as yet another reinforcement learning problem, but at a higher level, the level that chooses over W. And so here we made an instantiation of this idea where we just discretize W. In each component, you can have a 1 or 0 or a -1, and we can do Q learning to choose this higher level preference vector. And then we can do GPI at any given instant, given the W that we have, to decide what the policy should be. And this is the green line in these graphs. And you can see that that is better than Q learning actually in this case with the amount of data that we're showing. And it's also better than any fixed preference. And you can also do this one more step with temporal abstraction. So this is a paper we had at NeurIPS last year where we presented the option keyboard architecture. And the idea here is that we're also going to do GP and GPI, but this time instead of having policies, we're going to have options that include termination conditions. And if you think of termination as another action, you can kind of see that you can put options in this process very naturally. Initially, this idea of the option keyboard was suggested by Rich Sutton, but basically we instantiated it. And here are some results actually with an agent that is a continuous control agent in an arena. It trains some options in this red, blue, and green direction. But then using GP and GPI, we can actually solve tasks that require the agent to move in any of these yellow pie directions. And one thing that I want to point out is that compared to usual option methods, which are restricted to calling options from the given set, in this case, we are actually allowed to have other primitive actions because we're doing GPI. And again, GPI might decide to choose actions that are in none of the policies that we have. And so the results that we can obtain with this method, which is this blue curve here, are better than results that can be obtained just by calling options. So I'm going to wrap up very quickly. I've presented some very general tools for using policies and predictions that can be quickly combined to provide solutions to new problems. Again, you should view this as a trade-off between a way to make a trade-off between the solution quality and the sample complexity that may be useful for continual learning, never-ending learning kind of problems. There are lots of interesting open problems here. The biggest one in my head is what is a good behavior basis for a particular class of environments? I've showed you that the policies that we are using as a basis do make an impact, but we don't actually know what would be an optimal initial policy set. There's also an issue of calibration in some sense, because reward scales may be very different. Here we have some control because we're assuming that the rewards are obtained through this linear combination over features, and so we can essentially calibrate through the feature layer. But in general, that may be a problem. And I would really like us to also get more empirical experience with this method. So I'll stop here, be glad to take questions.
Fantastic, thank you, Doina. Let's open the floor up for questions. We have about 5 minutes for questions. Maybe I'll start then, Doina. Oh, there's also something on the Q&A, but
I'm not sure I can.
How about I will, this is Amir Masood. I will, Amir Masood Farahmand asks, why perform generalized policy improvement only for one step? So specifically, can't we add the new I prime to the list of policies, evaluate it and add it, sort of build this dictionary of policies incrementally?
Absolutely. And so this picture, picture B here, this is basically what we did, is we built the dictionary of policies incrementally, always adding policies. This is going to cost more data because anytime that I add a policy, I'm going to have to compute its successor feature representation. And so in principle, either I need to remember data from before and do off policy learning, or I need to run the new policy and get its successor feature representation because I need a value function for it. So that's the trade-off. If we were open to that, then we can absolutely grow the policy set over time and then continue doing policy improvement and have a generalized process as in normal dynamic programming.
Amir Masood, you can speak now as well, or I see Alec has a question, so maybe we can start there.
Right, yeah, sure, thanks. Thanks for promoting me to be on the panel. So I have another question, Doina. It's a very good work. I read some of the papers. So like here you take the supreme or maximum over all the policies, but does it make sense to maybe just take over a subset of policies, maybe those policies that are somehow more similar, to kind of make pi primes that are specialized to policies that are somehow similar? I don't know if it makes sense or not, but.
Yeah, so in principle, you could restrict the supremum to a subset of big pi, and then you would have an improvement with respect to that subset. Now, the similarity here is a little bit of a tricky thing, because what you want, like you could get, for example, very good generalization from policies that are very different than the optimal policy for your task. So if you imagine that you have two policies that pull you around the X and Y direction, and the third policy should go away from X and Y, right? These two policies are very different, but they're good enough to push you in Z.
Right.
Right. And so there's this other effect that's a little bit harder to quantify. I think it's a really interesting thing to think about, and it does go back to this issue of what's a good behavior basis, because you can consider this behavior basis given at the beginning, or if you were to construct the set of policies incrementally, you could also think of which policies you want to include at every step.
Okay. Thanks.
Hello?
So I was it was more of a comment than a question. Like you pointed out, adding the latest policy every time to the mixture has the problem that you have to estimate more and more value functions. A slightly different way of allowing yourself to do more than one step of policy improvement is to think of really using this as part of the gradient direction you estimate in a policy gradient method, where you take a few steps on policy, and then when you want to use a terminal value function, instead of using the on policy one, you use sort of the max function coming out of generalized policy evaluation. And we recently did some work using this style of approach. I mean, we were thinking about this more in the imitation learning style settings, but it's same policy improvement. And we found that way to be quite beneficial, especially if the policies you're improving upon are fairly suboptimal for the task at hand.
Yeah, that's a great point, and yeah, I'll have to read your work, but yes, I agree with your comment.
Emma, you next.
Yes.
Very interesting work. I was excited to hear the talk. I had a question about whether or not this issue of sort of which basis functions we use for the policies. Do you think maybe some of the recent work in reward-free exploration might be relevant there if we have very little assumptions, or if we think there might be very different types of reward functions we don't later? I wonder if some of that work might generate a series of policies designed to sort of cover the space that we could compute the successor representations for in the function approximation setting.
Yeah, that's a very interesting point, and I think that's one possible solution. One of the restrictions is we would ideally, so either we would like the space of policies to be small, or we would like the policies to be very related, because if big pi is very large, then taking that max may become expensive. And so, you know, I think this is where it becomes interesting to think, like, you know, how do you build that in? Like, if all I gave you is 5 policies, which ones? And clearly the policy set may depend also on this size. The alternative is also to consider the space of policies actually to be some other kind of, you know, maybe a continuous compact set that has some special structure so that maxes can be taken. But I'm not sure, like, that seems like a very hairy problem right now. So we're, you know, right now firmly in, you know, a small discrete set of policies. But yeah, the pointer is really good.
Great. Maybe we'll wrap this up now to move on to Sham. Thank you so much.